Hello everyone, this is Kiran Kumar from the Department of Mechanical Engineering, and today I am going to solve and discuss the Module-3 concept, that is the beams. Okay, so the beams, as you see, it is nothing but a member which carries the both bending loads as well as the concentrated loads, and usually the beams, if you want to define, the beam is a member in which the load subjected or load acted over the particular structure which is perpendicular to the axis of the system. Okay, like that we can define the beam elements, so or simply beam. This is how a simple configurations of the beam. I am not going to discuss much about the basic concepts. Okay, so coming to its the behavior, we already said, and then the next part is the types of beams based on supporting conditions. You are already discussed into that the cantilever beam is there, simply supported beam, overhanging beam. Okay, so many types of beams that we have seen based on the supports that we have adopted. Okay, so this is a simple example of simply supported beam where one end is pin supported and another end is having the roller support. Okay, so like that the support conditions are exist, and coming to its what we call the deflections quantities, we are having two deflection quantities. One is deflection in y direction, another one is angular deflections. Okay, that we are familiar when we consider any beams. So it may be deflect in this way or in this way, that is in y direction. Okay, and if since it is subjected to loading conditions, what is going to happen is it is having a deformed shape of this way. Okay, so that indicates that it is having the angular deflection also. So by the these analysis, I can say that it is having a linear displacement in y direction and angular displacement about z direction. Okay, so about z direction it is having the angular displacement. Okay, this is about the displacement part, and later on coming to the loads, we are having the variety of loads that will acted over the beams. Okay, so as you've seen, one is a point load that is being applied, another one is the uniformly distributed load. Okay, UDL, simply we call it as UDL, as well as uniformly varying load. In addition to that, the bending load. Okay, the bending load, as you see in this is, I can take it as a bending load, UDL and UVL and concentrated load. These are all the variety of loads that is acted over the beams. Okay, and thereafter, if you want to model this in the view of the FEM, so obviously I can discretize that particular. If I take this as my example itself, okay, I will discretize the whole structure into a single element which is of this type, so which is a 1D element once again. Okay, so we are having two nodes, so element 1 having two nodes, so node 1 and node 2, and for at each node we should define its displacements also. So as you've seen and as we said previously, so it is having the linear displacement first and after that angular displacement. Okay, so let's call the linear displacement in positive directions. Okay, since it is an initial considerations that we are doing, so let's take all the quantities related to the positive direction. Okay, so displacement in positive direction, as let's call that as q1. Okay, you can go for small letters, then it's good, that is q1, and angular displacement and q2. Okay, angular displacement at q2. Coming to the node 2, we are having two displacement. One is the linear displacement in positive direction, that is q3, and q4 in positive angular displacement, that is denoted by q4. Okay, so by this considerations, I can say that each element in the beam which is having 4 degrees of freedom, q1, q2, q3, q4, 2 is linear and 2 is angular displacement. Okay, that you should remember, and you should remember these what we call the sign conventions and the directions also. Okay, and later on as I said, okay, we should have the loading parameters. Okay, as I said, we are going to consider two load conditions, UDL and point load. So point load we don't have any what we call a problem, but in case of UDL, let us discuss that part. So if I take a beam element, UDL, if I am going to assume in the upward direction, okay, that direction part you have to remember. This is the ideal conditions that we are dealing right now. Why? Because for easiness in the sign convention, because so upward direction I'm taking it as a positive, no, that's why the load is also I'm going to take upward direction for our convenience. Okay, so if you want to model this to the beam nodes, that is as we've seen in the previous cases, the loads are usually acted, external loads are usually acted over the nodes. Okay, so that's why if I take the UDL is actually a surface phenomenon which is acted over the surface. So this I cannot model. Okay, I cannot consider this as a load. Okay, instead I should convert that so that it should acted over the ends only. Okay, that is at the nodes. So if I convert that UDL into the end nodes, then it becomes, okay, so like that we should always do that. If there is a small derivation for this, okay, we'll skip the derivation and look into the what actually happens. So if the load magnitude is P Newton per meter, then which is subjected to a length of element LE, if I convert that, then it becomes for each nodes. So if I am going to write down that as a force F in terms of my matrix form, so force F is equal to, we are having 4 quantities, 2 is at each node. Okay, so that is first one P LE by 2, second one P LE square by 12, and third one P L by 2, and the last one is minus P LE square by 12. So like that I can represent the loads which when it is applied in form of UDL. Okay, so F is equal to PLE by 2, PLE square by 12, PLE by 2 minus PLE square by 12. Okay, and representation that I can do that right now in this way, and it is representation is not much necessary in case of solving problems. Okay, so hope I will only follow this one and you also. And coming to the stiffness matrix of the beam elements which is of this type, so K is equal to EI divided by LE cube, okay, where LE represents the length of the element, and multiply by 4 cross 4 matrix where which is denoted by these quantities 12, 6LE, 6LE, 4LE square. Okay, so this as well as 2LE square. These are all the quantities that we am going to consider, where E denotes Young's modulus, I denotes mass moment of inertia, and LE represents length of the element. So hope here this LE, capital LE and small LE both are same. Okay, no need to confuse regarding that. And later on yeah, by considering only these factors, let's quickly go through one of the problem, okay, which is of this type. So this is a beam problem when one end is fixed and at few positions it is having the support conditions of a roller support, okay, and later on a 12 kilonewton per meter of what we call the UDL is applied to at particular this position, okay, and where I should find out the displacements and all, okay. So coming to the constants that are given, so length of the first part is 1 meter and second part is also 1 meter. Young's modulus and mass moment of inertia, sorry, area moment of inertia is 4 into 10 raised to 6 Newton per mm square. Okay, so this is the actual problem where let us discretize. If you want to go through the FEM formulation, the first step is discretization, where I am going to consider the axis first. This has x and here it has y, and I am going to take only two elements right now. First element should be straight, sorry for that, straight, and let us call this as element number 1, this as element number 2, okay, and this has node 1, this has node 2, and here it has node 3. In addition to this, I have to denote what we call displacements. So this has Q1, and here it has Q2, this has Q3, and this has Q4, okay, Q4, Q2 all are angular displacement, and here it becomes Q5 and Q6, okay. So in addition to that, I need to define the loads also. So F1, F2, F3, F4, F5, F6, okay. So like that you have to do the FEM discretization. Once it is done, let us quickly look into the stiffness matrix. Here we don't have much difficulty as we've seen it previously, okay, and okay. So for the first element, the stiffness matrix is as given below, A divided by L cube, L6 LE like this, of 4x4 matrix. And let's keep the same maintain consistency of units, where I'm going to take mm as my consistency. So length of the element should be converted to 1000 mm. Young's modulus 200 into 10 raised to 3 Newton per mm square. I, which is already 4 into 10 raised to 6 Newton per mm power 4. Okay, substitute that EI divided by LE cube and all those magnitudes. Either you can go for mm or else you can maintain the same meter as your units, okay. If I maintain the meter as unit, then this formulation, okay, the formulations that I am showing right now, they usually used the meter as their consistency, okay, for simplicity in this matrix. So here let's go for the same method only, where I am going to use meters right now. So E 200 into 10 raised to 9. So I will write down that somewhere here. So K1 equal to 200 200 into 10 raised to 9, 200 into 10 raised to 9 multiply by I, you need to convert that 4 into 10 raised to 6. Okay, so here 200 into 10 raised to 9 multiply by I value. So I value should be, okay, there is a small mistake, this one should be mm power 4, that's it. Is I is 4 into 10 raised to 6 mm power 4. So if I convert that, then it becomes 4 into 10 raised to 6. Okay, that is in terms of mm power 4 multiply by 10 raised to minus 3 whole power 4. Why it is 10 raised to minus 3? Because I just used milli. Milli is 10 raised to minus 3 to the power 4. Okay. So whole divided by length of the first element, that is 1 meter. So it becomes 1 cube. So if I use the meter, then the whole stiffness matrix will be in the simplified form. Okay, that's why I am using meter unit right now. So once this is done, let us substitute all those quantities, and although into we are having the length parameter in the matrix also. Okay, so LE, so 12, 6 into 1 minus 12 in minus 12, 6 into 1. Okay, like that if we do, then it becomes the unit itself multiplied by that constant. Okay, so once that matrix will be developed, so just multiply the value of 8 into the matrix. Okay, so that is for your convenience. So once this is done, the next part is the representation of the nodal degrees of freedom or global connectivity. So for element 1 consisting of Q1, Q2, Q3, Q4. Okay, that's why I can represent 1, 2, 3, 4 here itself. 1, 2, 3, 4 for each rows and columns. Okay, and let's calculate the stiffness matrix of the element 2. Okay, so for the element 2 also, all the parameters is almost the same. Okay, so that I am going to get the same magnitudes as EI divided by EAI divided by LE cube, even the matrix also. Okay, and once this is done, the only changes that exist is the global degrees of freedom or global connectivity. For the element 2, we are having Q3, Q4, Q5, Q6, that is 3, 4, 5, 6. Okay, 3, 4, 5, 6. Write down that for the each rows and columns. So once this is finished, the next part is the presentation of the global stiffness matrix, that is K is equal to K1 plus K2. Okay, so the size of this global stiffness matrix is 6 cross 6 because we are having 6 degrees of freedom. It starts from Q1 to Q6. Okay, so write down that. So as usual, you need to look into the element stiffness matrix. So 1, 1 and the positions or coefficients of each matrix. Okay, so 1, 1 we are having magnitude 12 and we don't have any connectivity 1 to 1. So it is 12 only. So like that for the 2, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. Okay, like that you have to do all these things. 5 to 1 we don't have connectivity, that's why it is 0. 6 to 1 we don't have connectivity, that's why it is 0. So if you do that, the only changes that exist is the highlighted one, that is the red one. So where there is a 3 to 3 connectivity. So if I observe 3 to 3 connectivity is 12 here, and if I look into this element stiffness matrix of the second element, here also we are having 12, 3 to 3 connectivity, that is 12. So that it becomes 24. And coming to the node, so 4 to 3 connectivity we are having minus 6, and 4 to 3 connectivity we are having positive 6. Okay, So that's why it becomes 0. Since it is symmetrical, the same value exists here also. And coming to the 4 to 4 connectivity, we are having 4 to 4 connectivity with the magnitude of 4 and 4 to 4 connectivity with the magnitude of 4. Therefore, it becomes 8. So only changes exist here. And later on, once the global stiffness matrix is finished, the next part is coming with the element force vector. That is, I should calculate the F. And coming to the element 1, we don't have any external forces, that is UDL as well as the point load. Okay, so that for the element 1, the force vector will be 0. So let us denote that by F1, F1, F2, F3, F4, all values are 0. But for element 2, we are having the 12 kilonewton per meter, and that's why I should go through this matrix where P equal to 12 into 10 raised to 3 and length of the element 2 is 1 meter divided by 2. Okay, so if you did that, then it becomes minus 6000 minus 1000 minus 6000 plus 1000. So one thing you should observe is about the sign convention. So this derivation what we did, or this force vector that you are observing, which is basically when we are having the upward force. Okay, so when we are having the upward force, that is P is positive here. But if I come to the present problem, so the UDL is actually in the downward direction. That's why I should include negative P. Okay, minus 12 into 10 raised to 3. Okay, so take care of that. That's why I am getting the values in negative sign. So once the F2 value that you have calculated, the later part is the combination of or finding global load vector. Okay, F is equal to nothing but F1 to F6. So how you did consider that? By using this what we call the FEM model. So F1 to F6. So here, so from the element 1 force vector, we don't have any F1, F2 forces, but from element number 2, we are having some magnitudes of forces F3, F4, F5, F6. So enter those values. So once global load vector is finished, then a later part is global displacement vector. Global displacement is nothing but Q1, Q2, Q3, Q4, Q5, Q6. So once it is done, the next part is having the equilibrium equation. So that is KQ equal to F. So consider all the global matrices, that is stiffness matrix, displacement matrix and force matrix. So enter that in the proper arrangement. Okay, once this is done, the next part is applying boundary conditions. Okay, so and apply the elimination method. Let us look into the given structure. So the left end is completely fixed. Since completely fixed, the Q1, Q2 value is equal to 0, and coming to the node 2 and node 3, there is a restriction in the direction Y, that is upward direction. Okay, so at each node 2 and 3, since it is having the roller support, it is unable to move in the upward directions, that is Q3 and Q5 equal to 0. So only thing that is left is Q4 and Q6. Okay, so Q1, Q2 equal to 0 at node 2, Q3 equal to 0 at node 3, Q5 equal to 0. So since all these parameters are 0, eliminate the respective columns and rows. Okay, that is first column, second column, third column and fifth column. Similarly, first row, second row, third row and fifth row. Okay, once you eliminated that, I got 2 cross 2 matrix with the values 8 into 10 raised to 5 A multiplied by the matrix 8 to 2 4 Q4 Q6 along with the forces in the right hand side. So if I solve this 2 cross 2 matrix, I am going to get Q4 as minus 2.679 into 10 raised to minus 4 and Q6 as 4.464 into 10 raised to minus 4. Note that the unit is not meter. Why? Because it is in angular displacements, then it should be radians. Okay, so hope this correction is also we need to have to do. So this is how we are going to find the displacements in case of the beam matrix, okay, or the beam problems. Hope everyone will solve these types of problems and try to practice more problems regarding this. By this problem, I am going to conclude my online lecturing. Thank you, everyone.